This is where we left off, and we were talking about the respiratory bronchioles that then lead into the alveoli. And the idea behind these, the alveolar ducts, the duct would be the tube that opens up into this alveolar sac, where you have several epithelial cells, and the epithelial cells themselves, so these sacs, these look like sacs of grapes or groups of grapes, are surrounded by capillary beds, so surrounded by blood flow, and also these fibers that are elastin fibers. And what happens is, of course, the capillary beds are there because the oxygen is going to diffuse out of the alveolar sac and into the blood, and carbon dioxide is going to diffuse, and diffuse is the correct word, it's a passive process, from the blood into the alveolar sacs. And they need to actually facilitate or help that air then go back up out of the conducting zone, so take the pathway back the way we just described, so from the respiratory to the terminal, to the secondary, to the primary, to the trachea, and then back out of either the nasal cavity or the mouth, the oral cavity, whichever you breathe through. The same pathway, and the sacs actually want to empty themselves, or they never totally empty themselves, but get themselves less full of gas. And that happens because of these elastin fibers. These elastic fibers look kind of like rubber bands that are around the alveolar sacs, and they expand and then recoil to help facilitate that getting air out. It's kind of an interesting thing, but it's also what happens with regard to somebody who has emphysema, where they have problems breathing air out. It's not so much the conducting zone, it's this respiratory zone that actually isn't facilitating, isn't doing its job to help, because it's been damaged to breathe out. So you have a duct that then opens up into several sacs. Those sacs are surrounded by capillary beds, and then you also have these elastin fibers that facilitate the expiration of air. And a nice picture here. I'm sorry, many times I forget I have a great picture, but just to refresh, in terms of, you have the duct coming into the sac itself. The whole thing is the alveoli or alveolus, depending on whether you're single or plural. This is the area where gas exchange takes place. This is what we consider the respiratory zone. So the respiratory bronchioles into this respiratory zone. Squamous epithelial lining, and then capillary as well as elastin surfaces in the alveoli. A couple of things that are associated with the alveoli are two specific types of cells. You have type 1 pneumocytes. Those are so you have simple squamous epithelium. That's making up you can see it here. It's kind of the pinky color. The alveoli, simple squamous epithelium. And then you have two types of specialized cells, type 1 pneumocytes, that are patrolled or are helped by the dust cells. And the type 1 pneumocytes are the epithelial cells, one and the same. And then you have type 2 pneumocytes that produce surfactant. And that's kind of where I wanted to be, is you have two types of cells, type 1, type 2. It's type 2 that produce surfactant. And surfactant is an important, if you in terms of preemies, it's important for you, but in terms of preemies, one of the things that is very important with regard to a preemie is making sure that surfactant is starting to be produced, because surfactant is an oily type secretion. Phospholipids and proteins And what it does is it coats these alveolar surfaces inside and reduces surface tension. So it makes it more likely that these alveoli will expand. There's less resistance, and so it's more, it basically greases the wheel, as it were. It lubricates, surfactant lubricates so that the expansion can happen, the elastic fibers, the recoil, back the other way. So those are pretty important cells. And also to understand, there are macrophages, dust cells in the lungs, because even though you have your cilia beating back, your mucus layer, you have your tonsils, things still get in the lungs. And that's, as I said, that's where a lot of bacteria love to be, in that dark, warm, oxygenated environment. In terms of the other image that you have here, it's something that we will talk about quite often coming up, but just to acclimate where you are, so you, the pinky portion, and I'm talking about the right image, the pink portion is the alveolus itself, so it's just taking that pink epithelial cell and giving you a little piece of it. And then the orange portion is blood. And so the orange, you have your plasma, and then you have a red blood cell there. And red blood cells, we know what they have. They have heme in them that actually can carry oxygen. So what's going to happen, and this is based on a concentration gradient. So oxygen is more concentrated in the air you just breathed in than on the red blood cell. So it's going to diffuse out of the alveoli into the capillary bed, and carbon dioxide, because this is blood that just came from the body, so deoxygenated, is going to be, and so it is more concentrated inside the blood than in the alveoli, so the two will exchange. You have, and this is diffusing based on a concentration gradient. And the other thing that we want to see here is how thin that connection is. It really is just 1 or 2 cells thick that gas is diffusing across, and then you multiply that by the size of a half a tennis court, because that's how much surface area this alveoli can make if you open them all up, all of the sacs up. And you have an excellent design for that gas to diffuse in. And even at this design, we'll talk about this in terms of how much of it actually gets off and offloaded and able to be picked up by red blood cells. So we look at, there are many ways we can look at the efficiency of this system, and you probably have had some of them done with yourself. We have spirometers. We also have pulse ox meters that are actually looking at, not only in some respects looking at red blood cells' capacity to carry oxygen, but also the body's ability to use oxygen. The events of respiration, and just like with dissection, I probably will repeat this more than maybe you want to hear it, but it tends to be the more complex part of this chapter, and so I do want to make sure everybody understands what we're talking about. Is the definition of pulmonary ventilation is the air moving in and out, and you hear this on the medicine shows all the time. They say ventilating. What they're doing is they're just putting air in and out. So ventilation is not respiration. Ventilation is basically making the raw products available for it to happen. Respiration can either be internal or external. External respiration is the exchange of gas between the pulmonary alveoli and blood, between blood and the pulmonary alveoli. We consider it as the breathing in, because the breathing in allows that air to get to the alveoli and then move on into the blood. Internal respiration is the gas is going from the blood to the cells. And so if that's oxygen, it's going to the cell, carbon dioxide leaving the cell and going into the blood then can be exhaled out. Remember, carbon dioxide is a byproduct of cellular respiration, and so all of the metabolic activities of the cell, so it needs to be given off and got out of the system. So respiration, you have ventilation and internal respiration and external respiration. In terms of respiration, internal and external, on the somehow or another I got this turned around. I'm sorry about that. You have O2. From here on out, almost every image, oxygen is going to be written as O2, carbon dioxide is CO2. And so on the right, you have external respiration, and these images come from your textbook, or they're very close to what's in your textbook. So you have this idea of oxygen binding to hemoglobin in the red blood cell because it has an affinity for oxygen. So the oxygen can diffuse through the alveoli into the blood, and it actually, because of the design of the pieces of those, the heme on the hemoglobin, the heme is the protein, the functional part of the protein, the hemoglobin protein, and it actually attracts and binds to that oxygen. It's a chemical attraction, binds to that and fixes it in a reversible way, but still fixes it. And carbon dioxide, which at that time was, some of it can be carried by red blood cells, but most of it is diffused in the plasma. So most of the gas is dissolved in the liquid portion of blood, which we call plasma. And so CO2 is going to diffuse out, and oxygen is going to diffuse in and bind to those red blood cells. And then the pulmonary, the systemic circulation is going to take over, and this blood is going to circulate throughout all parts of the body. When it gets to a cell that needs oxygen, which all of them will need oxygen, the oxygen, remember, it is reversibly bound to that hemoglobin. It's going to diffuse off the red blood cell because the body cell wants it more. It's depleted its own source of oxygen in all of its metabolic behaviors. So its concentration of O2 is less than the concentration of the blood that's coming by. So down a concentration gradient is going to cause that O2 to move into the cell. And the opposite is true with regard to carbon dioxide. This cell just performed many metabolic activities, so it created a good amount of carbon dioxide. That carbon dioxide then is going to diffuse out of the cell into the blood. That's internal respiration. And you have a nice image of that here, as well as you can see it in your book. Read through it a few times and then you'll get it down. It's not really that difficult. Then you have another image of internal respiration. What we're doing here is we're just getting a little bit more involved, I guess, chemically as to what's happening. And then again, what you see is, you have external respiration on the left, because we can start with the alveolar sacs. And so you have that oxygen moving from the alveolar sac into that red blood cell, and then hemoglobin is Hb, and it's forming a molecule called oxyhemoglobin. That's a reversible reaction again, and we call that O2 loading. So we're loading O2 onto the red blood cell. And then in the plasma, what you have is a bicarbonate ion plus hydrogen. So then you have carbonic acid that then disassociates into carbon dioxide and water. And that's basically what you breathe out. You breathe out carbon dioxide and water. And remember, you do breathe out H2O because you can see your breath in the winter. We will pick this up on the next one.